So now we're going to have a look at hypothesis testing for the mean, where we have a single sample of data. In AS, we have already had a look at this in some cases. So we've already had a look at the case where we have a large sample, a known population standard deviation, large sample and unknown population standard deviation, and a small sample and a known sample standard deviation. We've already had a look at these three, which is just doing a normal single sample hypothesis test. Now we're going to be having a look at what we do when we have a small sample and unknown population standard deviation, which in a similar way to what we've just had a look at with confidence intervals means that we're going to be using T instead of using the normal distribution. So as it says here, when we perform a hypothesis test for the mean, we have to perform the same checks as we did when we were finding the confidence intervals for the mean. So we have to decide whether we've got a large or small sample, and we have to decide whether we have a known population standard deviation or if we only have the sample standard deviation. And then in AS statistics, we had a look at the three different examples of when we use the normal distribution, which is Z. However, we now have a fourth case where we have a small sample and we do not know the population standard deviation. As with the normal distribution, if you are assigned letters to the groups, then we have to define them. This doesn't come up in the single sample, but it will come up later on. So now we're having a look at when we have a small sample and unknown standard deviation. As I said, the other three cases of this were covered in AS and can be found in the normal distribution hypothesis testing video. So if we don't know the standard deviation of the normal distribution, remember, even though it's a small sample, it still has to be normally distributed, then we need to be using the t-test. Now the actual formula for this is that we do the mean of the sample minus the mean of the population divided by the sample standard deviation divided by the square root of n. But we are going to be using our graphical calculator to do it. And as you can see here, it does have the standard deviation divided by the square root of the sample size in it, as we were talking about when we were having a look at confidence intervals. Now, because our calculator is going to automatically do this, we are not actually going to be applying the central limit theorem to our standard deviation. We are just going to be typing in the mean of the sample, the standard deviation of the sample, and the size of the sample. So that's quite important to bear in mind, that when we are typing this into our calculator, because our calculator is automatically going to use this formula for us, we don't need to do any changes to these values. We just need to find them. As always, we are, well, as some of the times, we are using the critical value booklet to find our critical value, our formula booklet. And this is going to be on page 19 of the formula booklet. And as it says here, the critical value for the t distribution is from the tables. In order to get this, we need to know the degrees of freedom. And if you remember back, we have talked about degrees of freedom before when we were looking at the chi-squared hypothesis test in AS. And this is going to be the degrees of freedom is going to be the number of pieces of data that we have minus 1. And you can see here down the side, just as we had with chi-squared, this little V symbol here stands for degrees of freedom. And across the top, in the same way as we did with the chi-squared, we're going to have to do the significance level taken off 100% to decide what value we are going to look down from. So we're going to have a look at an example, and we're going to start off with a two-tail test. Now, something that isn't written down here but is quite important to keep in mind is, in the same way as we half the significance level when we have a two-tail hypothesis test, with a one-tail t-test, we're going to use 100% minus the significance level for where we're going to look down from. However, for a two-tail test, so for a two-tail T, we're going to be using 100%, but we're only going to take off half of the significance level, because again, just as we had before, half of that's going to go below and half of that's going to go above. And it's quite important to keep that in mind, that when we're looking up our critical value, if it's a one-tail test, then we do just look down from 100%, take off the significance level. But if it's a two-tail test, we have to halve that significance level when we're taking it off. We are only going to do one example of this, so I just wanted to make that clear before we started it, as this is a change, it says here. So it's going to be a two-tail one, but bearing in mind that this is slightly different for a one-tail one. So here we have carrots are put into cans at a large food packing factory. The machine which puts carrots into cans is set so that the amount of carrots in each can is normally distributed with a mean of 200.5 grams. The machine is overhauled. Following the overhaul, 8 tins are sampled and found that the contents following weight of carrots. And there we have our sample. Investigate at 10% significance level whether the overhaul has led to a change in the mean quantity of carrots placed in each tin. So in the same way as we had with our single sample normal hypothesis test in AS, our H0 is going to be that the mean is still the same as before, so 220.5. And our H1 is going to be, because we're looking for a change, not an increase or a decrease, it's going to be that the mean is not the same as 220.5. And again, in the same way as we did in AS, we're now going to have to find the mean from the sample. But also, if we have a double check, there is no standard deviation given to us in the question, which means that we are going to have to use the sample standard deviation that's gained from the data. So it's important that we write that down as well. So first of all, we need to put the data into our calculator. So that's 224.5, 217.3, 222.9, 219.7, 223.1, 221.5, 225.2 and 221.4. That's too many twos and no decimal point. As always, double check that you have typed everything incorrectly into your calculator. Not even us mere mortal teachers get it all right all the time, so we always have to double check, because we are just going to be getting our answer from the calculator. So then we go into calc. We need to check our set. We only have a list of data, we have no frequencies, so this is the right setting, list 1, 1. And then we need to go into 1 var. So that gives us the sample mean of 221.95, a sample standard deviation of 2.57681974, and an N of 8. And that is very important that we don't round at this stage, in the same way as we didn't round when we were having a look at confidence interval, because we don't want those rounding errors to end up changing our test statistic. So then we want to go back so that we have all these options at the bottom. So it says graph, calc, test, intradist. And we're actually going to be going into test, then T, and then one sample. So just to state that again, we go into test, then we go to T, and then we go to one sample. And as you can see here, it's a little bit different than what we're used to. Our first option here, where it says mu, is wanting us to put in what symbol we have used in our H1. So in this case here, it's a two-tail test, so that's the correct symbol. But you can see that you can change the symbol using the F1, F2 and F3 keys in your calculator. So in this case we want F1, we want the not equal to key. The next option is where we need to put what value is also used in our hypothesis test. So you can see here that it says mu is not equal to mu naught, and then it's asking us what the value of this mu naught is. So that's this value here, 220.5. So 220.5. We are then being asked to enter the sample mean, the sample standard deviation, and the number of pieces of data that we have. So the sample mean was 221.95. The sample standard deviation was 2.5768194. Again, just quickly double checking that I've entered that incorrectly. And the number of pieces of data that we had was 8. And then when we click execute again, this value here, this t value, is our test statistic. So t is equal to 1.59 to 3 significant figures. You could write more of it down if you wish to, but 3 significant figures should be enough for us to do our comparison. So this was a two-tailed, so remember that is our test statistic, as I just said, 1.59. To look up the critical value, remember that we're using page 19 in our formula booklet. I have also put an insert of this on the previous page. And as I said, that was a 10% significance level, but it was a two-tailed test. So half of 10% gives us 5%. 100% take off 5% gives us 95%, which means that we're going to be having a look down from 0.95. Remember as well that we need to be looking across from our degrees of freedom, and in this case, as our n was 8, this tells us that our degrees of freedom is going to be 7, because our degrees of freedom is just going to be the number of pieces of data that we have minus 1. So we're looking down from 0.95 and we're looking across from 7, and that gives us this value here, which is 1.895. So our critical value is 1.895. And in this case with t, if our test statistic is smaller than our critical value, then that means that we end up accepting H0. So as the test statistic is smaller than the critical value, we accept H0 at a 10% significance level. There is insufficient evidence to suggest the mean quantity of carrots is not 220.5 grams. Remembering in the same way as we did with the normal hypothesis testing that we did in AS statistics, that when it's a two-tailed test, we are always putting not, and when we're writing our conclusion, we're always talking about H1, and that's why that happens. We're saying it's not, there's insufficient evidence to suggest that it's not 220.5. Now, something else that's quite interesting to point out, on this page where I got my test statistic from, on the calculator, this one here, we also have the information that I typed in, so the mean, the sample standard deviation and the n, as well as what my H1 should look like. Mu is not equal to 220.5, so there are two things that you should be checking, but also it has a p-value. Now remember, we use a p-value when we are performing a binomial or a normal hypothesis test, and by extension also the sign test. We can see here that the probability that this has occurred by random is 15.6% to 3 significant figures. we were having a test at a 10% significance level, which is obviously a smaller level than what this gave us. So that tells us that we were expecting to end up accepting H0. We still need to have a look at our critical value to make sure that we make the correct comparison, but this gives us a good indication that we have made the correct conclusion. The chance that we gained these values at random is 15.6%. We wanted the probability that this would happen at random to be less than 10%, so that means that we are accepting H0. There's not enough evidence to suggest that it's not 220.5. There's not enough evidence to suggest that the overhaul has changed the quantity of carrots being dispensed. And I think that's quite important to bear in mind. It's quite a good double check. Does the p-value support what I have found? Do I understand what the p-value signifies enough to be able to make that comparison? In this case, yes, 15.6% is bigger than 10%, which means I'm accepting H0. It wasn't rare enough for me to reject my H0. And that's a good way as well, in case you forget, which way around you do your accept and reject in this hypothesis test. As I just stated though, and I will write this down as well, if our test statistic is smaller than our critical value, we are going to be accepting. If the test statistic is bigger than the critical value, we are going to be rejecting. So just a couple of the assumptions. It's very, very similar to what we had when we were having a look at the confidence intervals. Because again, we are performing a hypothesis test here, the sample does have to be a random sample. This comes up quite a lot in terms of hypothesis tests. And also because it is a small sample, we do need the population to be normally distributed in order for our hypothesis test here to be valid. And again, these are the same as when we had the known sample standard, we had the known, population standard deviation in the small sample that we had a look at in AS. So I'd now like you to pause the video and give the Now You Try question a go. Remember to be careful to check if it's a one-tail or a two-tail test. And in your calculator, make sure that the hypothesis, the symbol that you have in your alternate hypothesis is at the top, followed by the value that you have in your hypothesis, and then it's the mean of the sample and the standard deviation of the sample and the number of pieces of data in the sample. Okay, so hopefully you paused the video and you gave the Now You Try question a go. So here we have bottles of wine have nominal content of 75 cl. That just means the amount of contents that they have. The volume of wine in bottles are normally distributed. It is suspected that the wine inspector that a particular vineyard is underfilling the wine bottles. The inspector takes a random sample of 11 bottles, so that's good. We've hit both of those assumptions there. It says that they are normally distributed. It says that they took a random sample, which are found to contain the following volumes. So we have our sample there. Investigate at 5% significance level whether or not there is evidence that the vineyard is underfilling its bottles. So our H0 is that the mean is going to be 75. Because we're talking about underfilling, our H1 is going to be that the mean is less than 75. From putting those values into our calculator, we get a sample mean of 73.9463636, and we get a sample standard deviation of 1.21110918. And again, don't do your rounding yet, because we are using these values to do a further calculation and we don't want those rounding errors to sneak in there. And we have 11 bottles there. Remembering that the degrees of freedom is going to be the number of pieces of data that you have minus 1. That means our degrees of freedom is going to be 10. So from putting that into our calculator, if I just go back one step, you can see what I entered. So again, like I said just previously, making sure that that symbol matches up with what we have in our H1. Making sure the value matches up with what we also have in our hypothesis, so 75. Making sure that we've entered the sample mean, the sample standard deviation, and the number of pieces of data correctly should give us a test statistic of minus 2.89. Now, in a similar way to what we did with PMCC and SRCC in AS, it's much easier to do our comparisons if we make our values all positive. So again, I've made it so that my test statistic is positive. So the size of my test statistic is 2.89. Remember that those modulus lines, the straight lines going down either side of the test statistic, means that we're looking at the size of the value, not the sign of the value. And from looking up our critical value in our critical value booklet, remember, like I just said, degrees of freedom is 10. And this time, because it's a one-tail hypothesis test, we're just going to look down from 0.95, 100% take off that 5%, which gives us the 1.812. So as the size of our test statistic is bigger than the critical value, this time we're going to end up rejecting H0. At 5% significance level, there is sufficient evidence to suggest that the mean amount of wine dispensed is less than 75 cl. And again, if you think about what I was talking about before, on this page here where I've got my test statistic in the calculator, double check, yes, that matches up with my H1 at the top. That's my test statistic next. Got our sample mean, sample standard deviation, and our numbers of piece of data. They all match up. But also we have that important p-value. This time our p-value, it's given to us in standard form, but that just means that we have 0.0081175, which as a percentage is going to be 0.81175%, which is definitely smaller than 5% this time, which again backs up the fact that we have ended up rejecting H0 this time, because the chance that we get these volumes of wine at random without having an actual decrease in the mean is a much smaller probability than the significance level that we were using to test it with. So again, it's a good measure of thinking about, should I have rejected H0? Well, yes, my p-value is smaller than that significance level, and it's just a way that we can double check that we have got this correct. Thank you very much for listening.